Yeah, so we started with transverse shear, and we said that we learned about transverse shear in previous classes. And as an example, we took a rectangular cross-section beam, prismatic beam with simple supports, but there are two moments at the end, and the cross-section is given here like this, right? And width is given by B, and depth is given by D of the beam. We said that the shear stress, we have learned that the shear stress distribution is going to be a parabolic distribution, and it is transverse shear because they act on the surface like this, right, with a smaller amplitude towards the boundary and a larger amplitude at the neutral axis. This is how it works, and the value for that, or the amplitude for that, is given by tau is equal to VQ by IB, and V is the shear force at the cross section of your choice. Q is second moment of area, right? It is a moment of area. From top the point where you want to find your shear stress, right? And then you have I. It's known as second moment of area. And then B is the width. This is what we learned, right? And we understood how to find for various kind of cross sections. This VQ by. While doing that, we made some inherent assumptions that we need to do for solving this kind of problem. Assumptions are: one, the effect of shear stress, shear force, let's say, is very, very minimal. That is very low. Otherwise, it will create warping, right? Okay, so that's one thing we need to understand, and we also need to remember. Okay, so how does the shear stress distribution happens? Second thing is we learned is shear stress distribution over the width is uniform. What does it mean? It means that if you have a cross section like this, right, and you have, this is your B and this is your D, then your shear stress distribution is constant at a cross section like this, uniform, right? But in reality, this is assumption, this is assumed. I'll answer your question. But in reality, what will happen is, if this is your cross section, then your shear stress distribution is going to be something like this. And this is what you get from your VQ by IB. This is VQ by IB. This is through advanced theory. Okay, so it's going to look like this. All right. So VQ by IB gives an average shear stress, gives average transverse shear stress. All right. Now this change in value between this average and the max. Let's say this is your max values. The max values are at maximum value let us call it tau max, are at the boundaries of for a particular y. Now, the study says that this tau max is 1.03 times VQ by IB for B by D nearly 0.5. But it is equal to 1.40 VQ by IB for D by D around 2. So that tells that if you have sections where your width and your depth are compatible, it was discussed earlier also, were compatible. In that case, your VQ by IB is good enough to calculate your stresses. But if you do not have that, then your shear stress starts playing a bigger role. Shear stress plays bigger role. Okay, so we should be careful in such cases, right? This kind of member, something like this, let's see a member. A member of this sort will create a problem. This is D. This is B. This member will definitely create a problem in your shear stress distribution. Okay, because the span or the width to depth ratio is quite high in these cases, so they will create a problem. But sections which are like this will hardly create any issue with your values, because the values will be 1.1 times VQ by IB, and most of the time we take the maximum VQ by IB, right? Maximum of the VQ by IB, and therefore most of the time they are safe in design, because we don't design for section by or y. For every y value we design for the maximum value, and therefore it is most of the time it is safe, and there is a factor of safety which also takes care of these issues. Okay, now my next thing is, have we seen sections like this before in our designs or in our analysis? Have you seen this before? Yes, we have seen this. We'll come to that, where we have seen this. And before that, do I have anything else to discuss about the assumptions? Yeah, another assumption is that for a non-rectangular boundary also, there can be issues with respect to the shear stresses, right? So for sections like this, okay, for section like this, you will always have issues with your shear stress calculations at these locations. To be governed using advanced theories. Okay. Also for sections like this, although these are rectangular sections, these locations should be careful with stress concentration factors. Okay, those things you have to make sure that you have some ideas. Yes, most of the cases for B by D greater than 2, there will be issues with shear stress distribution. What we do in cases like this, if I have a beam which is like this, okay, an I section. If you look at this part of the section, the D by B ratio here is going to be quite high. And therefore, we have to worry about it. We cannot directly use the formulas that we have because that's not going to give us the accurate solution, right? It will give us a solution, which will be an approximate solution. We'll be happy with it also, because when I design a cross section, I will not design that cross section based on the values that I get at those areas, right? We will design the cross section based on the values that we get in the maximum point of view. Okay, so I'm not going to design my cross section based on these stresses. We will design the cross section based on the stress here, right? So this one is going to have shear stress like this. Okay, so let us draw that. Right, it's going to look like this. And my design is this value. Not this value. And therefore, if there is an increase here like this, doesn't matter to me. It doesn't matter. But one thing that matters is how do you check this thickness? How do you calculate this thickness? Okay, let's look at something called, therefore, there is something called shear flow, which you have to understand. How is the shear flows from one portion of the beam to the other portion of the beam? Now, let us pay attention back to what we used to draw. Let's say that we have a beam again. Don't think it's a deep beam or a big beam. It's just exaggeration of the picture so that it's quite well. The cross section here is an I cross. Okay, is an I section. Now let us take a portion of this from here. Let's say this is dx distance apart, and let us draw that I section in that dx distance difference. So let's say we draw that I section. All right, I have to make a small opening here and then draw something like this. Same thing should be here. Very nice. Thanks for accepting this diagram as a part of your teaching. Okay, very nice. So that's the portion of I section. I hope this is all right and well acceptable for you. Okay, that's an I section. Okay, having drawn this, now these two sections will have some moments here, right? Acting. This will be M, and this will be M plus dm, right? So here there is a M moment. Here there is a dm, M plus dm. Okay. Now look at various points on the beam. Let's look at a point which is this one. Let's say this is B. This one, let's say this is C. Okay. Let's look at B. The thickness here is T, very small, and from the center of this till the center, not the end, center of that, from the center of this is D. Okay, and this is also T thickness. Let's tell it's T. Okay. So this B point and C point are very interesting points. So if I take a small portion around this B point, let's say I want to look at the portion which is like this. And then I would like to look at the portion which is around this. Okay. So this B portion B portion around B. Okay, very nice. So the portion around B is going to look like this. Right? This is your point B. Okay. Now, if you look at that section here, this is a flange, right? And the flange is supposed to take a lot of moment. That portion is supposed to take a lot of moment, right? So as for a small distance here, for a small deviation here, there will be a lot of moment difference, right? And that moment will create stresses, and there will be a lot of stress difference. So here there will be a stress F that will be acting here, and here there will be a stress that will be acting is F plus df, and this is your thickness T, right? F plus df. And on the top portion of this is free surface, so there is no stress that is acting here. And the bottom portion is also free surface, right? There is no stress that will be acting here. So top portion is free surface, bottom, below it also a free surface, so no stress is acting there. Therefore, to balance this F and df, there has to be a force that will be acting here. Shear force. This is again df. Okay. Now, since there is a shear force that is acting here in the df, there's to be a transverse or complementary shear that has to act, and that complementary shear is going to be something like this. Clear? So this is df, and that is your complement. Okay. Now this shear, the shear that I drew here, this one is acting on this surface. Okay, not surface, inside here. So at this boundary here. Okay. If I draw a similar point for C, similar portion for C, similar portion for C, I'll have the same drawing. Okay, this is your portion C. Now in this case, this side is F, this side is F plus df. But what about the other side? This will not be on this side, right? That will be on the other side, because this side is a free surface here. Okay, so the other side is going to be inside there. It's going to be df. Okay, and since that is also going to look like this, so there will be one shear that will act like this here. So if I draw the I section, Draw the I section. This is point C, this is point B. So in C, it looks like this. And in B, it looks like this. You might get confused, so I'll put double. Okay. And the verticals here, we know how to calculate on which direction it's going to go. So verticals here is going to be like this. Now, again, if you take points, portions at the bottom, you will see they go like this. So if you see this properly, it's like water flowing, right? It's like water coming from this end and also from this inlet. Both the inlet water comes and they join somewhere here and then they flow down and then again they separate at this point and go one go this outlet, the other go to that outlet. Okay, this flow, this flow of shear is called shear flow, and it's written as small q, which is equal to force per unit length. Why per unit length? Because if I extend now my understanding of this section to complete this portion of dx and understanding of that section to this complete dx portion, then this is, if I write it as q, is equal to df dx. Okay, so that's called shear flow. All right, so now if you want, I can write this as this distance as dx. Okay, so that's called shear flow. And it's like a flow of water or flow of a liquid from the inlet to the outlet. But how do you calculate now the Q? Okay, how do you calculate Q? We know how to calculate shear stress, and we know how to get force from shear stress, just multiplying by area. Therefore, shear flow is going to be, you don't have to, you have to just integrate it once, right? Or you don't divide. So your shear stress is given by shear stress tau is given by V Q by IB. Shear flow Q is given by VQ by I not no width. Okay, so units are different. All right, so this is shear flow, and you can do shear flow for various cross sections as you want, and they all will be of similar kind. So but how does shear flow change through a cross section? Let us do that. Let us analyze an I section and draw the shear flow for an I section. Shear flow for an I section. Now if I draw an I section here, okay, I know my shear flow is going to go like this. It is 0 here. It is 0 here because that's the boundaries, right? So this should be 0 here. Q equal to 0. Q equal to 0. Right? Similarly, here also there are boundaries. So here also Q equal to 0. This is also boundary, Q equal to 0. Okay. Now here the shear stress goes like this. And here the shear stress go like this. And then they join and go like that. Okay, now what are the values that we have at each of the cross section? Let's look at one cross section that is here. That is somewhere a little distance from the boundary. So let us look at this point. Okay, and this is my neutral axis. Remember that this distance is d by 2. Okay, let us look at this dx here. And therefore, when I calculate shear stress, I calculate based on the portion that is above it, right, from 0 to that point. If you remember, we have done it earlier. So this is my point to calculate my Q. So shear stress small q is given by V capital Q by I. Okay, clear? Okay, now V is known. That's going to be V by I is also constant. I is for the complete cross section. What is Q? Q is the moment of this portion, right, with respect to neutral axis. Now, what is the moment of the area of this portion with respect to neutral axis? So what is the area there? Area there is, if this is my B, the full thing is my B, then that is going to be B by 2. So it is going to be, and this portion, let's say, is the distance that I am looking for. Okay, so let's say that is small x. So its area is going to be B by 2 minus small x, right, into thickness T, because the thickness here is, I have taken T, right, and its moment with respect to neutral axis, the moment with respect to neutral axis is going to be into D by 2. So this is area and this is moment arm. From,
sir,
1 minute, neutral axis, right? So it comes out to be finally as VTD by 2I into B by 2 minus X. So the point that I want to make here is Q varies linearly with respect to X. If I have to draw that section, let me take this section, copy and put it again. If I draw that section again and my thing is going to vary linearly, right? So let me put a different color here. It's going to vary linearly like this. It is 0 at this point and it should be linearly maximum here. So it go like this. This is going to go like that. And similarly here also, but here it will be in opposite diagram, right? Like this. Okay. In this section, it is going to be opposite to it. So it's going to be like that. You can draw it both sides. Some books will draw it on both sides. Some books will draw it at the bottom side like this. It depends on how you draw, but it doesn't matter because the direction is given in the arrows here. Okay, same here, like this. Same here. The triangles, I'll write it here, otherwise you'll ask questions. The triangles can be drawn above the section, but make sure you draw the arrows properly. Okay, so now you can ask me questions. I would be happy to answer questions on this.
Sir?
Yes?
So the previous slide, sir. So can you please explain this Q part again, sir? This Q part.
Q part, yeah. Yes. So when we did for rectangular cross section, how did we do? if you remember when we did for rectangular cross section, I'll come to a rectangular cross section where we did it. Yes, probably. What did we do? We calculated shear stress. Yes, here. For rectangular cross section, what would we do? If we are looking at a shear stress at this value, what did we do? We calculated the moment of the area above it, right? And we said the moment of the area above it is considered because this portion is 0. So you have a baseline here. So from here to here, the shear stress calculation is based on the moment of the area of this portion, right? Here also, we are trying to do the same thing. Here also, we are trying to do the same thing. Now, since the flow is on this direction, I have to take this point is 0 and then move like this. And therefore, you're looking at the moment of this portion of the area, right? With respect to the neutral axis. Okay?
Okay, sir.
That's why the Q is calculated area of this with and its momentum with respect to that.
Sir, and also here we took the area to be uniform with respect to volume also. Like, so we didn't integrate and we directly wrote the momentum, right?
Yeah, because you know what is the area going to be here.
Okay, sir.
Right? And what will the Q max value here? Q max value is known to you.
At x equal to 0.
Max value here. You can find, right? You know 0 here and it's linearly varying. So how much it's going to be? You know that, how to do that. So x is equal to 0. So it is going to be, x is 0, it's going to be Vt d by 2I into d. Okay, so that's how it's going to go and that's how it's going to look like. Now, what about this portion? Wave portion. Wave portion, you already know how to calculate, right? It is going to be square parabola. Only thing is you cannot multiply, we cannot divide by b. It should be, q should be vq by I, right? So it's going to be tau into b. It's simply going to be tau into b, right? So this portion is going to be tau into b. So I'll rub this also. That portion is going to be oh no, it will not be, it will not start from 0 because there is already q max value there, right? So it will start like this. Okay, this is q max in flange. So I will write that q max flange. Okay, this is your q max wave. And q here, q is equal to tau into. So that's called shear flow. And shear flow is force per unit length. It is not stress. It's the shear that flows. Now the use of shear flow is very important for design. Now there are a few things. Shear flow varies linearly.
Hello, sir.
Yes.
Sir, that B has to be the this bit, right? Not the actual B.
This B. Oh, okay. B wave I will write. Is that clear now?
Yes, sir. Yes, sir.
Okay. Now points. Shear flow is parabolic along the direction parallel to load. Shear flow is linear along the direction, along the normal to the direction of the load. Perpendicular or normal the direction of load. Parallel or tangential, both. Not tangential, parallel or inclined. What I'm writing, I cannot inclined or parallel to the load. Okay, this is very important. So here in this case, we have assumed that the load is acting this way, right? Therefore, this is parallel to the load, and that is going to have a parabolic distribution. Whereas this is perpendicular to the load, and therefore it will have a linear distribution. Okay, that clear? And remember that these are all possible because we have assumed T, thickness T is much lower than B or D. Okay, that assumption is very important. T is much lower than D or B. Okay, so it's called thin walled section.